Hello students, my name is Shahab Ali Asghar Nami and I am serving as Associate Professor of Chemistry at Department of Industrial Chemistry, Aligarh Muslim University, Aligarh. So in continuation of our previous lecture where we have talked about the elution chromatography and the various concepts which comes under the elution chromatography, most notably the distribution constant, the retention factor, retention times, different retention times, selectivity factors, etc., etc. So we have discussed them, and we will be using them in our coming slides. So today we are going to start a brand new topic, that is the zone broadening and column efficiency. So the efficiency of any column with regard to chromatographic separation actually depends upon zone broadening with regard to elution of a particular solute from a column. Now in this series of lecture we are going to discuss the zone broadening and the efficiency in terms of certain parameters, and we are going to study this zone broadening in terms of two closely related theories which we are going to discuss in the coming slides. So let us briefly sketch the outline of the topics which are to be covered in the lectures to become. So first of all we will study the concept of separation and of course the efficiency of a column with regard to zone broadening. Then we will go through the column efficiency with regard to a theoretical concept that involves certain plates, certain imaginary plates in the chromatographic column. Then we are going to quantify that concept, that theoretical concept, into an equation that is called as the Van Demeter equation. And the Van Demeter equation actually involves three terms, A, B and C. So we are going to study these three terms in detail, and we will study the impact of this A, B and C in terms of Van Demeter equation. Then we will move towards the optimum flow rate, that how we are going to optimize different conditions so that we can have a better efficiency in terms of separation of an analyte, and that efficiency can also be seen in terms of, can also be defined in terms of a curve. Similarly, after going all this, then we are going to study certain applications of this Van Demeter equation in terms of the separation by using the gas chromatography, by using the high performance liquid chromatography, and of course after that we will study one by one certain factors which affect the column efficiency, then some real life applications, and of course at the end we are going to study the advantages, the disadvantages and some of the key points which are very important and very interesting. So let us begin our journey of the zone broadening. So initially we have to understand that about the nature of the curve, that how this curve actually gives you information about the elution of certain analytes through a given column. Now we know that initially what happens is, first of all we should understand that this elution of certain substances which are to be separated they actually come out of the column in a range of time. That is, the separation occurs in a range of time, that is, maybe if you can say, that is starting from t is equal to 0 to t is equal to 10 minutes. So that is in a range of time. That is, the elution occurs in a range of time, not at a single point of time. For example, if you think that your solute is eluting at a single point of time, then you will obtain a graph like this. That time is written here and the detector response is here. Then if the elution is occurring at a single point of time, then you will get a peak like this, a straight line perpendicular to the time axis. This actually, if this is the case, then it tells you that the solute are having no interaction with the stationary phase. because the moment they start interacting, they have to spend some time, and the moment they spend time, they will give you a curve. They will give you a curve. Now, this curve, the shape of the curve actually tells you about the rate of migration, about the about the different velocities which the different solute particles at which the solute particles are traveling. Now, ideally speaking, a curve should be like this. Ideally speaking, your curve should be like this. Now, this curve is generally called as the Gaussian curve. Gaussian curve or normal error curve. This can also be called as the normal error curve. This curve actually is important in the sense that this part of the curve is called as the fronting. This is called as fronting part or front part of the curve. And this actually tells you about the solutes which are moving at a very fast rate as compared to their other neighboring molecules, and because of their faster rate of migration, they are eluting initially. So, this forms the first part of the curve, and this is called the fronting part. Similarly, the solute molecules which lag behind, which are eluting after a certain time or after retaining more, after having a more interaction with the stationary phase, they are going to elute at a later time. This part of the curve is called tailing part, tail, okay, tailing part. This is the tailing curve or tailing part. While the mid part, this tells you about the average velocities of the solute particles forming the central part of the Gaussian curve or the central part of the curve or the peaks, you can say. So, in the first figure, you can see that a broad curve is obtained enveloping two peaks, and an ideal separation should give you the best possible resolution. Okay. So, an peak becomes an ideal if it is resolved. Number one condition, that you get a resolved peak. Number one condition is that you get a resolved peak. Okay, that is, it should be separated from the other peak in a very well manner, which you can see here. And the number two condition is that peak should not be broad. That is, ideally speaking, you have slim peaks. The peak width should not be too much. That is, ideally speaking, you have a sharp peak like this. Ideally, that is what you have to do. You have to cover, actually, you have to take in mind two things. Number one is that they should be separated as much as possible. That is, there must be no overlapping like in this case, and the peak width, that is the peak width, should be kept as small as possible. So, if you get overlapping peaks, then it implies that you get actually poor resolution. It implies poor resolution. So, in the second case, you can see the peaks are well separated. They are well separated. If you draw perpendicular like this, that is actually, they are well separated, and sometime we are going to study, this is called as delta Z, and that is very important to describe the efficiency or to describe the effectiveness of any chromatographic column. Okay. So, you have to keep two things in mind. Number one is that the peaks must be resolved and the peak width should be as small as possible. That is, you should get, ideally you should get sharp peaks. Okay. So, you have minimum band broadening and you have maximum resolution. These are the two important factors which we have summarized here, that is maximum resolution, and this is denoted by RS. Similarly, we have minimum band broadening. Now, the efficiency of any column with regard to band broadening can be best explained by considering two theories of band broadening. These two related theories are called as, number one theory is called as the plate theory. Plate theory. And number two is called as the rate theory. We are going to discuss the rate theory in very detail, but just I am trying to give you a concept of, at this point of time, plate theory. Plate theory was actually given, this concept was given by the genius of their time, that is the Martin and Sinch in 1941. And even in fact, because of their breakthrough theory, and this theory is purely a theoretical concept. It has nothing to do with the experimental approach. And the beauty of this theory is that although it is a theoretical concept, but the terms which this theory defined was later used in rate theory, which is actually an experimental concept regarding which explains the band broadening. So this plate theory actually talks about the number of theoretical plates. Now, what is number of theoretical plates? Let us briefly just summarize it. According to the plate theory, concept of plate theory extended by Martin and Sinch, what they considered that a column is actually made up of continuous plates. They are made up of continuous plates. Okay, they are made up of continuous plates. Your chromatographic column. So it is made up of continuous plate, and each plate is further divided into a stationary plate, half of stationary plate, and half is the moving plate. That is half of the stationary phase and half of the mobile phase. And we know that the stationary phase, this phase remains fixed, and the mobile phase keeps on moving. So what they actually proposed, that for example, if you introduce your sample which contains, for say, 200 molecules, 200 solid molecules, the moment you inject them, so this 200 molecules goes to this plates, and these plates are actually continuous in nature, that is one after the other, and they are discrete. They are continuous and they are discrete, that is they are arranged in a one by one manner, in a continuous manner, that your column actually contains these plates, and each plate is divided into a stationary plate and a mobile plate, that is a stationary phase and mobile phase, and on each plate equilibration has to be done. That is, equilibration has to be done. For example, if you introduce 200 solute molecules, then 100 will be distributed here and 100 will go to stationary. Then these 100 will travel to the next plate, and there 50 will be remaining here and 50 will get distributed in the stationary. Then 50 will go backward and 25 will remain here and 25 will get here. So it's actually continuous movement of your solute molecule across these theoretical plates, and these theoretical plates are actually purely imaginary plates. What you have to keep in mind, that ideal columns or the practical columns does not contain any plate. They are actually hollow. They have the packed column. These plates are purely imaginary in nature, and this concept is to actually equate these plates in terms of the resolution, in terms of the band broadening of the column. Okay, band broadening is actually the response of the detector. Okay, so we have seen it. This band is actually originated from the detector response with regard to time, and this is actually the elution pattern. This is actually the elution pattern of your solute molecules. So this concept of theoretical plates actually originated, and in each plate you can see that there is an equilibration, and half of the molecule goes to stationary phase and half goes to mobile phase. So the solute keeps on moving downwards, and after a certain period of time it gets eluted. And here the detector is connected, and you actually get the detector response here. Detector response. Okay. So you get a detector response. Now, how actually these theoretical plates are connected? Now let us see. So let us suppose that the height, let us suppose this height is called as H, is called as height equivalent to theoretical plates. Sometimes it is also written as HETP. Okay. So this packed column, actually, this packed column contains n number of theoretical plates. It contains n number of theoretical plates. Selectivity we know. Selectivity we have already discussed. Selectivity is K of, for example, if you have a two component system, then it is called as KB upon KA, the distribution constant of B upon A, where B is actually that solute which is eluted last. Okay. We have already discussed this selectivity in our previous slide, and we have also discussed retention factor also. That retention factor we have already discussed. So now we are actually trying to quantify this number of theoretical plate concept with this one. So one thing which we have to keep in mind, that the next theory which we are going to discuss, that is called as the rate theory, which gives you a quantified idea of the band broadening, uses the concept of HETP. It uses the concept of number of plates. Although these two concepts originated or proposed by the plate theory given by Martin and Sinch, but your rate theory is going to use it. So this is how this band broadening is defined by the continuous equilibration of your solute molecules over the passing of them through a column, and this you actually recorded it. So this band broadening is goodly explained, betterly explained by this plate theory. But the one important aspect of rejecting this plate theory was that plate theory does not give mechanistic explanation. Mechanistic explanation about band broadening. That is about the resolution, because band broadening is actually related with the resolution of peaks. So what happens is this: now you can relate the two things, that is, greater the number of theoretical plates, greater will be equilibration and greater will be its resolution. Okay. So you can see that what you can write at this point of time, that n is equal to L upon H. We are going to study this equation, in coming slides also. So that is actually n is equal to L upon H. L is the length of the packed column. This is length of the packed column to this one. Okay, length of the packed column, and H is the height equivalent to theoretical plate. That is HETP. Simply, sometimes it can be written as H. Similarly, you can, in terms of quantification, you can also think of resolution as 1 upon 4 of under root n. N is the number of theoretical plates. Alpha, selectivity, upon K dash, that is the retention factor. So if you want to quantify it, you can write like this in terms of equation: 1 upon 4 under root n, alpha minus 1 upon alpha into K dash upon 1 plus K dash. Now experimentally it has been observed that for all those separation where resolution is greater than 1.5 is good, that is, there you get there you get actually non-overlapping peaks. You get non-overlapping peaks. So you have to keep two things in mind, that for attaining the best you can say efficiency, what you have to have, you have the maximum resolution and you have the minimum band broadening. That is, this distance must be kept low and this distance must be kept high. So this must be kept as high as possible and this distance must be kept as low as possible. Okay. Now, one important aspect which we want to emphasize at this point of time, that this plate theory, because all these explanations which we have given here is with regard to plate theory. We have not come up to a rate theory. So up to this point of time, you should note that plate theory does not account about the velocity of the mobile phase. There is no factor. Nothing is, dependent here with regard to plate theory. So let us move forward and let us have a very specific idea about the band broadening. So you can see three different colors giving you three types of band broadening. So you can see blue color is telling you about the initial zone, the yellow color is telling you about the intermediate zone, and the broad zone is depicted by the red color. Now this red zone is, you can say, it is the column is not efficiently working, is not efficient. And this blue is actually an ideal curve, it's ideal. So in most of our experimental studies we find this, because you cannot ignore the non-idealities in flow, the non-idealities in terms of diffusion and the equilibrium. Although we are saying that at each imaginary plate there is an equilibration, but it is not so. Okay. So at this point of time, what is important to emphasize is this, that even in ideal column, diffusion comes into play. And we can see that this diffusion gets maximum when we are dealing with the gas, where the gas are actually acting as the mobile phase, which we are going to see when we are going to discuss the gas chromatography. So mind that we cannot, sometimes we have to take all the factors into account and we have to actually modulate it. So what we have to do, we have to restrict the widening of solute zone, because it leads to broadening, and we cannot minus the non-ideality factors in flow and of course in diffusion. So what we have to do, we have to have as resolved peaks as possible, keeping in mind that this peak width is to be controlled, or this peak width is to be seized as seized as possible. Okay, but we cannot overcome them. Ideally speaking, practically speaking, they exist. Okay, so what are the consequences of this zone broadening? Now the first and the foremost consequence or the effect is that the moment you get a broad band, you never know how many different solute it has engulfed in it. For example, in this case we have seen that this is actually solute 1 and this is solute 2, and that this broad band has actually enveloped these two. So you cannot have a good resolution. So resolution is not good, you cannot quantify it, because this, if you are going to extrapolate it like this and like this, then this area becomes common. So you cannot quantify. Quantification is not possible. In overlapping peaks. Similarly, if the resolution is not good, then the quality is also affected. So loss of quantitative accuracy because of the overlap of the adjacent peaks. And of course, the resolution is poor because you already get a broad band. Now the common examples is that you cannot, if for example if some impurity is there, you cannot separate it. Let us suppose that TR of your paracetamol is 5 minutes, and unfortunately that of your impurity is 6 minutes. Then it becomes difficult for you to separate, unless and until you have a very efficient column. But at the same time, if your column is efficient, then you can purely get 5 minutes, okay? Because now if you have an efficient column, it will actually make a distinction between the paracetamol and that of impurity. Okay, so this will happen provided your column is efficient, it is long enough, because we have seen that n is equal to L upon H. So if you want to improve the resolution, then you have n as far as as long as possible and H as small as possible. That is, the theoretical plate must be as small as possible and the length of column must be as long as possible, so that you can have an ideal column where you can separate the different peaks with regard to their elution pattern. So what are the major causes? So the major causes of zone broadening are eddy diffusion. What is eddy diffusion? We are going to study in the coming slides. Then the longitudinal diffusion and the resistance to mass transfer or mass transfer resistance. So where it comes into play and why eddy diffusion occurs? It occurs because of the multiple paths taken by the solute molecules within the column. And why this longitudinal diffusion occurs? Because of the spreading of the solute molecules in all directions, that is, from high concentration region to low concentration region. Okay. Now eddy diffusion, it is because of the multiple paths. So let us first discuss these in one by one. So let us first start with the longitudinal diffusion. What is actually longitudinal diffusion and why it happens and how it actually affects it? So these are actually, if you just coming back to the previous slide, these are the parameters, that is A, B and C. These are actually the parameters of Van Demeter equation, which we are going to discuss in very much detail. That Van Demeter equation is HETP is equal to A plus B upon U plus CU. So it composed of three terms. A is the diffusion, eddy diffusion, B is the longitudinal diffusion and C is the resistance to mass transfer. So what we have to do, this HETP or H, to have a better resolution, it must be kept as small as possible. That is, H must be as small as possible to have the best resolution. That is RS. What we are doing is that we are trying to have a very efficient column, and in doing so, in order to have an efficient column, the height equivalent to theoretical plate should be as small as possible. And at the same time, it can also be said in another way that greater the number of theoretical plates, better will be its resolution, because that n is equal to L upon H, where L is the length of the packed column. We have already discussed it. So now let us take these three one by one and we are going to discuss them in detail. And what this smaller particles and uniform packing mean to us, we will discuss this also. So at this point of time, what we have to do, we have to minimize this HETP as much as can. So this can be minimized by minimizing A, this can be minimized by minimizing B upon U, and this can be minimized by minimizing Cu. So what we have to do, in order to have HETP as small as possible, we have to have all these three factors, that is A, B upon U and Cu as small as possible. Okay, so now we have to look in terms of minimizing these, these three factors, that is the eddy diffusion, longitudinal diffusion and the resistance to mass transfer. So let us take these one by one. Let us first take the longitudinal diffusion. This longitudinal diffusion is represented by the term B upon U, where B upon U, actually in B upon U, U is the mobile phase velocity. It is the mobile phase velocity. And now actually we are discussing this comes under the rate theory. This comes under the rate theory. That is, under the rate theory is defined by Van Demeter equation. Now the beauty of this theory is it gives you a quantitative idea of band broadening. Okay, so this rate theory actually talks about two important things. Rate theory talks about, number one is the random walk. It talks about the random walk of solute molecules. And number second point, the most important with regard to rate theory is that it talks about, or it accounts the mobile phase velocity. Mobile phase velocity, or you can say the rate of migration. Now let us suppose you have a column. Let us suppose you have a column. Let me draw a column which is a little bit wide. Let us draw like this. Now let us suppose that you introduce your mixture. Which is to be separated. This is the column, and you introduce mixture which is to be separated. The moment you add mobile phase, what happens is, the solute molecules, let me draw another one, the solute molecules will start moving along the mobile phase, and they will move in all directions. They will move this direction, this direction, this direction. They move in a random manner. They move in every part of the column. Okay, so they diffuse, your solute diffuse in almost all the direction, and this diffusion actually give rise to the illusion of these particles at different points of time, and it leads to zone broadening. That is the broadening of your peak. It leads to broadening of peaks. Okay. Now if you consider your mobile phase as gas, then this random movement becomes very high, because now gas has a very high diffusion. Okay, so this longitudinal diffusion becomes very important when we deal with the gas chromatography, because in gas chromatography the mobile phase is always a gas, an inert gas, and the gas has the highest diffusion and the solid has the lowest diffusion. So here because of diffusion, these particles take random paths, and because of the taking of random paths, they elute at random times, and because of the random time elution, your band actually broadens, and this gives you, then that actually leaves your separation inefficient. Okay, so in order, what you have to do, you have to restrict the band broadening, you have to restrict the band widening, you have to restrict it, and this can be restricted by increasing the mobile phase velocity, because the moment you increase it, then these particle, for example, if you increase the mobile phase velocity, then these particles will be directed more towards the bottom of the column, that is towards the bottom, which is connected to the detector. So what you have to do, you have to increase the velocity of the mobile phase, so that they can move further fast and their dispersion can be minimized. Now this actually dispersion can also be related from the Taylor's dispersion theory. Okay, so what you do at this point of time, in order to avoid this band broadening, you have to increase the velocity. But mind that your Van de Meter equation, if you remember, it was H is equal to A plus B upon U plus Cu. Now the moment you increase it, the moment you increase the velocity, if velocity is increased, let us suppose, then B upon U will be decreased, good, very good. But the problem is that Cu will increase, and overall these three will increase, and the increase in 3 is the increase in H, and the increase in H implies that your resolution is compromised. So what is the answer now? The answer is itself there, that you have to increase in an optimized manner. That is, your velocity, your mobile phase velocity should be optimized, and it must be towards the higher side, keeping in mind. So you can see this is depicted here, that is, if your velocity is low, then the diffusion is very high, and you can see that this is a very broad band. Okay, but at the same time, if you increase the flow too much, then of course you get a very slim peak. But again, if you increase it too much, then this Cu will increase. So you have to have a medium optimum velocity where the band broadening is not too much, and you can also control Cu. So this is actually the interplay of the mobile phase velocity. So you have to optimize it, not you have to take a very high velocity, because it will increase Cu, and at the same time you cannot have a low velocity, because if you have a low velocity, then this Bu term will increase and more diffusion is there, and the band will be broad like that is shown by the red line. So you have to have an optimum velocity so that you can get this yellow curve. So an example is that in GC, where you always have a mobile phase as the gas, then what happens is the diffusion occurs, because the gas has the highest diffusion, and because of the high diffusion you get broad peaks, and broad peaks means that your efficiency, your column is inefficient, it is not resolving the peaks. Okay, so you have to keep in mind about the velocity. So rate theory, which was given by Van de Meter equation, gives an idea about the velocity. So it gives an idea about the velocity. So with this, thank you very much. Thank you all.